Okay, so in this video I'm going to be going over the chain rule first of all. So the chain rule, and then I'll be going over some problems using some example problems of combination of the chain rule and product and quotient rules. So first of all, let's just start off with a simple problem that uses the chain rule. So we can say y is equal to the square root of x squared plus 1. So we got one function inside of another function. So we got a composite function here. So first thing I would do is assign u equal to the inside function, which is x squared plus 1, and that y equal the outside function, which is just the square root. So it would be u to the 1/2. So now we could just differentiate both of them. So we could say du of dx is equal to 2x, and dy of du is equal to u to the negative 1/2 all over 2. Because when we differentiate this, we want dy of dx. That's what our main goal is. And with this Lebniz notation right here, the du of dx and dy du, it's really going to guide us towards this, and you'll see that in just a second. So the du of dx times dy of du is equal to dy of dx, and that's what we wanted in the first place, because these u's cancel out and you're left with dy of dx. So du of dx we said is equal to 2x. We multiply that by dy of du, which we said is u to the negative 1/2 all over 2. This is going to equal 2x times u to the negative 1/2, all of this over 2. But we said u is equal to x squared plus 1, so we're going to say 2x times x squared plus 1 to the negative 1/2, all this over 2. And that's your final answer. So y prime is equal to that 2x times x squared plus 1 to the negative 1/2, all this over 2. And that's generally the chain rule. So you want to set the inside function equal to u and the outside function equal to y. And then you just want to differentiate them and let the Lebniz notation guide you, It'll just work all out in the end. The only time I wouldn't use the Lebniz notation is when you have a composite function with more than two functions. So like if you have like cosine of x to the square times the square root of x squared plus 1. I mean, you're going to have to do that a couple times, and that's when I really wouldn't recommend this. This is good for just like 2 composite functions, not 3. So that's one thing I wouldn't do. That's one thing I try to avoid. I'll just try to use the inside-outside rule. Just go from the outside and work your way in, differentiating it, and eventually it'll all work out. It's pretty easy. I know just with simple ones like this, I usually get confused, and that's why I let the Lebniz notation just guide me on these ones. And we'll do one more example problem real quick, just to make sure we have a good feel on this. Because it really, as soon as we got this, then any differentiating problems are pretty easy. So now we got this. We can use sine of x squared. So you can say y is equal to sine of x squared. Let's do the same thing. We set u equal to the inside function, which is x squared. Then you let y equal to sine of u. So then we just say du of dx is equal to 2x, and dy du is equal to cosine of u. And then we just do the same thing. We let the Lebniz notation guide us. So du of dx times dy of du is equal to dy of dx, which we really just wanted dy, the derivative of y with respect to x, of sine of x squared, and that's what we wanted in the first place. So we said du of dx is equal to 2x times dy of du, which we said is equal to cosine of u. But we ain't done yet because we said u is equal to x squared, so we can say dy dx is equal to 2x times cosine of x squared. And that is 2 examples of the chain rule. I'll do one more. And I think, it's pretty straightforward. My recommendation is just to keep doing it. And like I said, just let the Lebniz notation guide you, because eventually these